Good morning, everybody. This is the last module in the Manufacturing and Design class, MDT 201. And we are going to take a look at design for manufacturing. Um, what our aim is with this last module is to put all of the information that we learned in the beginning of the class in terms of production and manufacturing and processes and materials and put that together in a cohesive framework that a designer or a design team can use in order to chart a course for what type of material is going to be used in a product, what type of manufacturing operation may be used or may be recommended to be used in a product. Um, so so what we have in this module are I've broken it up into three different lectures. The first one, lecture number one, is the role of the designer, and we'll start that in a second. Um, I'll make a video going through all three of these, lecture one, lecture two, and lecture three, because these are not in your book. Okay, this is kind of outside of the book or in addition to the book, but really this is the culmination of what we were talking about. And I mentioned this earlier in the class several times about how what our aim is with this class. So without further ado, let's go ahead and get started. So lecture one, we're going to look at the role of the designer. Okay, so a couple of obvious things right here. All products that exist have been designed at one point. This is, kind of an obvious thing, but it's worth remembering. Every type of product that you see, touch, feel, buy, and unless it's produced by nature, it's going to be produced by man, which means it's been designed. And that means that all of these products, because they've been designed, they've also been manufactured. Okay, so depending on whether it's a small shop, a medium shop, or a large scale assembly kind of automated environment, all of these products that we touch and feel and purchase and see have been designed and they've been manufactured. So it's kind of an obvious thing, but I think it also bears note because there's a lot of mundane things that we see around us that actually, when you think about it, some group or somebody sat down to design this. There's some drawings associated with it, and somewhere it's being manufactured somewhere. So we're going to start off by looking at the design for manufacturing decisions. Okay, design for manufacturing is kind of a strange phrase because what else are we going to design it for? Well, but designing for manufacturing, as we'll see in these lectures, carries a lot of weight and a lot of built-in kind of information and history and knowledge and process. So we're going to look at the different steps that are that we find ourselves when we undertake the role of the designer and starting to design products or things for manufacturing. Step one in that design for manufacturing scheme or process is to start to design the overall structure of the product. Okay, so if we're designing a stapler, if we're designing a speaker, or if we're designing a computer mouse or an automobile, whatever we're designing, we always start with the big overall assembly or the entire thing in mind. All right, that's how we think of things, and that's how we think of mechanisms and assemblies and stuff. So the first thing is to get a good handle on the overall structure of the product. Then we want to start breaking out and identify what the materials are for that we're going to require for each one of these. Is it going to be plastic or metal? If it's going to be metal, what type of metal? What are the properties that we need for that metal? If it's going to be plastic, again, what are the properties that we need? This is an important concept, but notice the iterative, the arrow for the iterative feature of this. Iterative simply means that these are decisions that are going to be going around and around and around until we come up with some quote unquote best idea or best options or alternatives to move forward. So iterative simply means that we're going to make decisions and then we're going to reevaluate our earlier steps in light of the new decisions. And so this is kind of a feedback loop, all right? And we kick ourselves out of this when we decide that we have the best or appropriate or most appropriate materials in this case. Decision number 3 is how we're going to get those products, okay? So we design the overall structure of the product, then we kind of get a framework for the materials that we're going to be using for that product. And then we have to ask ourselves, well, are we going to make all of these component parts or are we going to buy them? And if we're going to buy them, where are we going to get them from? So obviously in many things that are designed, it's really a combination. There's things that are made by the company or by somebody. They need to be made. Or we can buy them, kind of like standard parts. So in either case, we have to identify what the product-specific parts are going to be, the things that we have to make or the things that we have to have people make for us. And then we also have to identify what the purchase parts are going to be. You know, these can be screws and nuts and washers and retaining rings and mundane things like that. It could be gears. It could be, you know, more complex. It could even be sub-assemblies that we purchase from other companies that go into our assembly. All right. So that's decision 3 that we need to make. Then we come into decision 4, which I've kind of split out here. So decision 4, if we're looking at purchase parts, we need to select those purchase parts. And if we're looking at product-specific parts, i.e. parts that we design and we make, then we need to design those product-specific parts. And notice now we also have an iterative loop coming back into here because, well, once we're designing these product-specific parts, we need to understand and get a framework for the materials that we want to use for these new parts. Okay, so again, another iterative feature here, another feedback loop. And then finally, for the 5th decision, we have to determine the assembly process. So how are we going to put all of these things together? And you know, it may or may not be obvious, but the assembly process actually has a feedback into how the parts are going to be designed to a great extent. You know, we can design things that can't be assembled. So we have to be careful. We have to constantly be evaluating whether our designs are going to work in the next step. And then if we feel like they're not or they're not optimal, then that provides a feedback mechanism into previous steps so that we can fine-tune that. So again, we have another iterative feedback loop into here, back into here, and back into here. So, you know, the whole decision-making process here is very iterative. There's a lot of back and forth and a lot of, you know, 2 steps forward, 1 step back. But that's just the nature of design and engineering design. Okay, so those are our 5 decisions for our design for manufacturing process. So what is the role of the designer in this? Okay, or role of the design team, we could say. Well, with an iterative process, the small decisions early in the process can have a large effect later on. Small decisions that appear inconsequential or not a big deal can have great ramifications later on. Okay, so that's one thing that we need to be aware of. Decisions later in the process can require redesigns of earlier decisions. Okay, so because we decide to do something one way later in the process, it will go back into earlier decisions or can reach back into earlier decisions. Proper planning, that is thinking ahead, can minimize these redesigns, because these redesigns, there's two factors here that are not optimal. They're not good for this redesign kind of process or kind of thing. Is one, redesign extends the time, okay, which in today's shortened time frame for getting things to market, producing things can have a negative effect. And the second factor here is redesigns cost money. Okay, they cost money through the extended time, but they also cost money because you can waste a lot of equipment and planning and materials and whatever with going down a dead end, so to speak. And finally, a robust design process will always iterate towards the best solution. All right, and that's why a robust design process means essentially that we want this iterative, these feedback loops, this iterative nature of it. It's actually good. In the same way that we produce better designs the more people that are involved in the design. And I know sometimes we don't feel that way, but generally speaking, the more people involved, the more that we plan ahead and have an iterative feedback loop to our designs, this produces a robust design, and it's going to be the quote unquote best solution. Good product design is difficult and time consuming, says the guru on the mountain. But bad product design is expensive and can kill companies. So, what do we design for? When we're designing something, what is our end result? Obviously we want a product. We want the product to sell, but how are we framing or constraining our design process? Do we design for function? Do we make sure that the part works properly or the product works properly? That obviously needs to be the case. We don't want to sell things that don't work properly. Do we design for aesthetics, making it look good? So this would be, do we design with the appearance more important than the function? I think most people would say no, but these are trade-offs that we have to do. Designing for function sometimes can lead us to products that don't look so good, but they work great. Obviously, vice versa, we could design things that look fantastic, but they don't work so good. Do we design for assembly? That is, do we design something so that it can be put together very inexpensively, very easily, very cheaply? Look at IKEA furniture. It's designed for assembly. It's designed for shipping and assembly. Okay, probably more for shipping. That's where IKEA kind of got their niche market, was in being able to flat pack ship just about any of their furniture. So that it can fit in storage containers that can be transported, via large shipping containers and rail cars and all that good stuff. Or do we design for manufacturing, right? Do we design a product so that it can be manufactured easy? Now, you can actually say yes to all of these things, right? And you can prioritize them. You can say, well, we want it to function. That's the most important thing. But it gets dicey when you start to break it up and to really come up with how each role is going to be assumed in the product. I think it's safe to say that we would want all of these things to be what we design for. And so the designer really has a lot of influences, a lot of considerations that they have to weigh. And at different points, priorities are going to shift, and one will take the forefront and the other will take a backseat. And then, they'll reverse later on. But the designer has to be conscious of, obviously, the consumers, who they're designing for, marketing. How well the product can be marketed is going to a great extent, determine how consumers take it on. They have to design for management, make sure management is happy. They have to design for accounting, meaning they can't produce these extravagant, $1 million products that nobody can buy or wants to buy. And then obviously designers have to design for manufacturing. Ultimately, we have to design something that is going to be producible, manufacturable, and this includes assembly. So there's a lot of factors here that we have to take into consideration. So in the modern day industrial manufacturing, there are a vast number of processes. We've gone through many of these. We certainly have not exhausted the list of processes, and there's new processes being developed every day, every week, all over the world. There are countless variations in each one of these processes. If you think back to casting, we maybe went through a third. I showed you a hierarchy of all the different casting operations there are for metal and plastic. We maybe went through a third of those. Okay, so there's more variations in there, and I'm sure that that's not an exhaustive hierarchical list either. There's limitations and variations with each one of these processes. So the sum result here is that comprehensive knowledge is nearly impossible, right? You can't be an engineer, a designer, a technician, and know how everything can be produced, whether it's metal or plastic, all the variations. So it's not something that we can do. So the challenge for designers is to know enough of each process and to make rational and informed decisions based on that limited knowledge. So we know the basics. We know what a forming operation is, what a casting operation is, generally speaking. We know what a forging operation is. We know how to do machining, or what a machining operation is, and so on and so forth, the sheet metal bending. So we have a good framework there. The specifics, we don't know, but that's okay. We don't need to know all that. So we're going to look at the manufacturing process hierarchy. Okay, so how do we break down the manufacturing process in a hierarchical framework? At the top of the list is the manufacturing principle. Okay, this is the highest order, the big picture view of the manufacturing process. This is what is possible according to the laws of physics. Okay, if you melt a metal and make it a liquid, then when you cool it, it solidifies into a solid. Okay, and that's what we call a forming operation. Okay, then we have the manufacturing method. All right, so we're going down a level. The manufacturing method is what is possible in practice based on the principle. Okay, so here's where we take that forming operation and we get a little bit more specific based on practice, based on that principle. And then finally, we have the manufacturing equipment. So we're chunking it down even lower. So now we're kind of at the ground level, right? We start up high at the 30,000 foot level, manufacturing principle. Then we come down to the mid-level manufacturing method, and now we come down into manufacturing equipment. And this is what is possible with the equipment used for that method. And in some cases, in the shop that you're in, okay? So for example, we look at metal casting. Okay, metal casting would be the manufacturing principle. Then going down a level to the manufacturing method, that would be the specific type of process: sand casting, die casting, investment casting, so on and so forth. And then going down to the ground level, then we have that sand casting machine over there in the corner of your shop, right? That may or may not have different features on it, but it's specific to what you have available. All right, so that's our hierarchy: principle, method, equipment. Um, some of this we've been through, that we've actually, all of this, I think, with the exception, I think I put additive manufacturing in here, but there are 4 classes of manufacturing products: processes, which describe the method used to change raw material or an intermediate part into a desired final shape; joining, separating, forming, and the new one, which we haven't talked about in this class, additive manufacturing, which is 3D printing. Okay, some of these terms are a little bit different than what we've seen, than what was discussed in the book, and I think I talked about this a lot with the book. The book that we're using, they use certain terms that other books will speak of differently. The main idea is not to get hung up on the exact term that's used. The main idea is to understand the process, and then you'll be able to see, oh, they're calling it this, instead of separating. Some books call it a cutting, or they call it subtractive manufacturing, to make a point of the difference between that and additive manufacturing. Okay. So I have what I have here is just a little breakdown. So what the industry generally calls it, and again, generally, but what the industry generally calls it: joining, subtractive, forming, and additive processes. Joining would be your welding and fastening operations. Subtractive would be your metal cutting. Forming is either casting or forging. And then additive would be 3D printing. And so how I felt compelled to do this, just so there was we try to cut down on as much confusion as we can. In your textbook, assembling would be what the industry refers to as joining. Okay. Separating and subtractive are the same. Forming, casting, and molding. So your book has 3 categories: forming, casting, and molding, and those would be what we in the industry call forming operations. And then the book doesn't discuss additive, so that's the cloud right there. All right. So from this point forward, we're really going to focus on the 3 shaping processes. Okay. The one that we're leaving out here is the joining process, where it's going to be welding or fastening things together. That's going to be shifted towards kind of the assembly role, which we're going to talk about in the 3rd lecture. Okay, so right now we're just going to be looking at forming, subtractive, and additive, or forming, separating, and additive. So limited discussion will be joining and finishing, okay, and assembly. Okay, so looking at the different principles, remember we're talking about the manufacturing process hierarchy. So the different principles are the shape casting of metal, sheet metal forming, extrusion of metals, forging, machining, injection molding, thermoforming, resin transfer molding, additive manufacturing, and then joining and assembly. These are suited to different types of materials: plastics and metals and other materials. The top grouping is what we would call a forming process. These are also forming processes down below that. And then right in the middle, we have the subtractive process, and then we have the additive processes. So again, just another little breakdown so that you can try to get a sense of what we're talking about here. And then finally, the joining processes. So what we're trying to do here with the manufacturing process triangle is we're trying to match our product requirements with our process capabilities, right? What we want on the left, which is product requirements, what we want our product to do, to achieve, to be able to do, and how we can achieve that through our production processes, right? How we can make the part flexible yet strong, resilient to Mother Nature, resistant to corrosion, all those different requirements, we have to figure out how to get those built into the product through the production process. And ultimately, we'll find that match. So successful design is really an optimization problem that involves a lot of trade-offs. Okay, so optimization basically means there's too many variables for us to take it all in. There's thousands and thousands of variables and decisions that go into product design. So we can't get a handle on those. So what we have to do is we have to identify the ones that are most important or that we feel most important and try to drive towards optimizing those, making those the resonant factors. And those are all going to involve trade-offs. The important thing is here, we're not going to find the ideal best answer. We're going to find the best answer for the time being with the materials that we have, with the processes that we have. So that's an optimization process and where the trade-offs come into play. So what we're going to be doing is we're going to be matching up our materials with our designs and with the processes that we have available to us. And so this leads us to really a what we would call a structured approach, or the need for a structured approach. A structured approach simply means that if the process is so challenging, if there's so many variables and so many different ways that we can frame it, that we can look at things, it cries out for a process, a structured process, a step 1, step 2, step 3. Do this in this order. Because that's going to give us the best chance of producing the quote-unquote best option or best object, and also, or best product. But also it gives us a chance to go back and look at things historically and say, yeah, this didn't work out so good. Let's change this next time around. So when we have a structured approach, a plan, a process, that's really how we get to this optimal solution for this optimization problem. So part attributes are defined and organized according to quality, function, and cost. Okay, the manufacturing process is going to be selected based on these 3 factors. These are the big factors that override all process choices or production process choices: function, quality, and cost. Part function asks, can it be done, right? And how? Part quality, can it be done well? Can it look good? Can it function good? And part cost is, can it be done cheaply, right? And of course, these 3 attributes, quality, function, and cost, compete for dominance. If you ask different people within a design team, within a design company, within a manufacturing or engineering company, depending on their office, depending on their status, they may answer which is the most important differently. So trade-offs are a necessity. All right, so let's go a little bit deeper into this manufacturing process triangle: quality, function, and cost. So when we talk about function, all right, part function, what are we talking about? What are the attributes of the functional attributes of a part? Well, it could be the materials. Okay, what is the part or product made out of? It can be its shape, right? That has a role to play in the function of the part. It could be its size. It could be its production volume. And it can be how it, quote unquote, looks and feels, the look and feel of a part. All those are part of the functional attributes of a product. Okay. Turning our attention to quality, all right, what are the attributes of the quality of a part? All right. That could be its tolerances, whether it has close tolerances or loose tolerances, whether it rattles around when it's moving or makes a lot of noise, or whether it purrs like a kitten and really is feels well made. What does the surface feel and look like? Is it rough? Is it smooth? Is it glossy? Is it high? Is it a high quality material, or does it look spotty and maybe there's a little rust on it? Are there defects in it? What are the properties? And what are its reproducibility? That is to say, if we make 1,000 of these parts, are they all going to be the same, or is there too much or a lot of variation within the quality deriving from the manufacturing process? All right. So, for example, if we compare subtractive, which would be machining, and additive manufacturing, which would be 3D printing, in terms of reproducibility, one of the drawbacks that 3D printing or additive manufacturing has is that it's not as reproducible as a CNC machining operation. CNC or machining in general is extremely reproducible. That means if we make 1,000 parts on the same machine, those 1,000 parts are going to behave more or less identically. All right, they're going to have material properties and they're going to have functional properties that are more or less identical. Okay, if it's produced to print. All right, 3D printing, we can produce it exactly to print, but the problem is there's a lot of variation within each process. Same 3D printer, right? But for a metal or plastic additive manufacturing process, there's going to be variety or little bit of differences here and there, which can be big problems. Okay. And the last attribute we're going to look at is the cost attribute. So how does the cost attribute break down? Well, in this we're talking about what is the part price? What is the investment that we need to make it, right? So if we're doing injection molding, the investment is, well, we got to make the dies, and that can be a very expensive factor. What's the time to market? How long is it going to take us to manufacture these? Do we have to have a whole assembly line put together? Do we have to have robots? Do we have to have trained personnel? Or can we just do it in a weekend? What are the social factors involved in that? And ecological costs. So with large production, we could have waste. Some of the waste cannot be good for Mother Nature, ecologically damaging, fluids. There may be environments that are dangerous. So all these factors go into the cost attribute. Okay. So when we look at everything together, the product manufacturing process triangle of quality, function, and cost has a lot of different sub-attributes along each area: function, quality, and cost. All of those come into play when we're choosing our manufacturing process. Okay, and this just touches on how challenging it can be to identify a manufacturing process, because we have to take into considerations many of these factors right here in order to figure out what the quote-unquote best manufacturing process is for a part or a product. Okay, so that is lecture number 1, the role of the designer. We will, or I will, get into lecture number 2 shortly, and we'll continue on this road and try to get a framework for making these decisions. All right.